All right, so now one thing that the last thing I was talking about before I left was all the stuff with co-state estimation and with pseudospectral methods. One of the questions I got this actually from one of the students remotely, who's not in Gainesville, is the question about how you actually do all this stuff. I mean, how you actually implement all these things when you're trying to solve a problem. And I think there's some confusion because all the derivations I did was to lead up to a final result so that all of you could see what the co-state estimates were relative to the Lagrange multipliers of the NLP. So what I'm going to do today is I'm going to do something that I don't generally do, but I'm going to do it anyway because I think it'll help all of you, which is I want to show you how all of this gets mechanized in a nonlinear programming problem solver. I can't obviously write lots and lots of code out, but I'm going to try to explain it in steps so that all of you can see the relationship between the nonlinear programming problem and these schemes themselves. I mean, the schemes are nonlinear programs, but how you actually would do it in the context of I have an NLP solver sitting in front of me. What do I need to do in order to be able to make that NLP solver solve the problem that I'm interested in solving, right? We'll do it with Redao. All of the other ones look almost exactly the same, but I'll do it with Redao. So this is the NLP formulation of Redao collocation. Okay? It's not that hard. It's really not. But it requires some thought. Okay? So in order to make this tractable, the way I do things is when I'm dealing with the nonlinear program or the nonlinear programming problem, my vector of variables is always denoted by z. I don't denote it by x because that just gets confused with the state of the system where you got x dot equals f of x. So I call it z. So in a nonlinear program, the general nonlinear program, the problem is to minimize f of z subject to a bunch of constraints. Bless you. G of z equals 0, and h of z is between some h min and h max. All right, where z is an element of Rn, and it's called the NLP decision vector. This is the terminology that's used in the NLP decision vector. All right, that's the nonlinear programming problem. Okay, that has nothing to do with pseudospectral methods or any type of complication. It's just a nonlinear programming problem. All right, this problem has a solution associated with it, which can be solved by any NLP solver. In the examples I sent you a couple of examples of how to do this with the pseudospectral methods, and then I sent you the code, or the MEX file anyway, for the NLP solver SNOpt, which we have a license for here at the university. So I sent it to you so you could run it and you could see how it actually works, in practice. Now the question is, what's the relationship between this problem and the problem that you would solve if you were going to solve this using a Redao pseudospectral method? So you remember that in the Redao pseudospectral method, so what we did was that the cost, this is the continuous time cost, is approximated by this thing I call Jn, which becomes phi of x1 t0 x n plus 1 tf plus, and then I get, because I'm scaling this, now I'm going to do this all on t0 to tf, so you can see how this all plays out, which is that you get a scale factor of tf minus t0 over 2, and then you get the sum from I equals 1 to n of wi times li, or I should say L of xi, ui, and ti, where ti itself is a function of tau, but actually, you know what, let's just write it that way, comma tau I, and then t0 tf. That's the approximation of the cost. Now, you can see that the cost consists of an approximation to the Mayer cost plus an approximation to the Lagrange cost. These quantities right here, Wi from 1 to n, are the LGR weights. They're the weights associated with the quadrature that comes from using Legendre-Gauss Redal. All right? The dynamics get approximated by, so you want to minimize this, subject to the constraint that the dynamics d times x 1 colon n plus 1 is equal to f 1 colon n, where this thing here is equal to the right-hand side evaluated at x1, u1, all the way down to the right-hand side evaluated at xn, un. Okay? And so these are the dynamic constraints. You also have a set of path constraints and boundary conditions. The boundary conditions have the form phi, which is a function of x1, t0, xn plus 1, tf, if they're equality or equal to 0. And then you get path constraints that say that c, evaluated at xi, ui, tau i, t0, tf, have to lie between some c min and c max, where I goes from 1 to n. Now you can see that it doesn't have the form of this nonlinear program over here, right? Because clearly these vectors, remember the way I define these things, xi is the approximation to the state at each of these points, right? Right? Where these are scalars, well, remember that these approximations come from the fact that I'll do the same thing for ui. Right? Ui equals u1 I up to umi, right? Where these values for the state come from the approximation that I used, the Lagrange polynomial approximation, right? Where I said that the state x of tau is approximated by capital X of tau, which is equal to the sum from I equals 1 to n plus 1, xi, li of tau. And these Lagrange polynomials, li of tau, are equal to the product from j equals 1 to n plus 1, where j is not equal to I, of tau minus tau j, all divided by tau I minus tau j. All right, so this part of the stuff here is not in this nonlinear program. You've already done the approximation, and you've come up with these equations over here. This approximation is taken out by saying I'm going to take the derivative of this, set it equal to the right-hand side, and I'm going to construct these collocation equations, right? That's what you get. Now, the question is, these are not vectors, right? If I string out x1 colon n plus 1, I get x1 all the way down to x n plus 1, right? They're clearly not vectors. They're matrices, right? But there's no difference between this and a vector z. The only thing is that how I'm shaping it, right? If I take 6 elements, right? I can string those 6 elements out into a column vector. I can also put them into a 2x3 matrix, right? It's the same number of elements, right? It's just the way I'm representing it is different, right? If I have numbers 1, 2, 3, 4, 5, 6, I can either have a long column vector which goes 1 through 6, or I can have 2 rows where it goes 1, 2, 3, 4, 5, 6. It's the same information. It's just represented differently, right? So in the case of the discretization, which is over here, I'm representing things by vectors and matrices. Over here, I've only got a single vector. So the question is, how do I relate what's over here to what's back over here? Because my NLP solver is going to solve this problem. It's not going to solve the problem in that form. It can't solve the problem in that form because it's expecting the input to be a vector. It's not expecting the input to be a bunch of matrices. You can't make it be a bunch of matrices. So you have to somehow relate what's over here to what's over here. So the way this gets done is actually quite straightforward. It's not hard, but it takes a little bit of time to actually sort of get yourself into the mindset of how this works. Now, if I embellish this NLP a little bit, Z actually lies between some Z min, I'll put it down here actually, such subject to Z between Z min and Z max. This is actually kind of implied in the NLP, but I'll state it explicitly so that we can see it, all right? So that you're dealing with the bounds on the variables too. So now what I need to do is when you now I'm going from math into more into implementation here, all right? So what is it that the NLP requires? Requirements of the NLP. One, I need an objective function. And when I say objective function, I'm not talking about computer code. I need to code an objective function, right? That needs to represent that function over there, f of z, right? Two, I need a constraint function. Okay? That constraint function consists of, one, equality constraints, and inequality constraints. Okay? These are the functions that I need to code. So now let's assume, for the sake of argument, that I can just lump G and H into one big function, all right? Because from a coding standpoint, all this can be done in just one big function. So suppose we say let, I take G of z and H of z, and I call the whole thing K of z, all right? So K is just a big vector, which is all my equality constraints and all my inequality constraints all stacked on top of each other, all right? So that's all it is, right? What I need to do now is I need to figure out how this function, which is my cost, this is my cost function, right? Which over here is represented by f of z. So the question is, how do I take the information here and map it to there? So the way we start is this, is that if you look at the functions, you'll see that I have the state. So what are the variables? What are the variables? The variables are xi, where I goes from 1 to n plus 1. I've got ui, where I goes from 1 up to n. And then I have t0 and tf, right? Because they're also variables in my NLP, because neither t0 nor tf may both be free, right? I may have a free final time, I may have a free initial time. So now what I do is the first thing we do is we notice that x1 to n plus 1 is a matrix of size n plus 1 by n, right? That's what it is, right? And while u, 1 to n, is a matrix of size n by m, right? Because I have m values under control. So now the question is, how do I get that back to this NLP decision vector? So what we do is, if we look at this matrix, we see that x, 1 colon n plus 1, could be written this way. y1 up to yn, where y sub j is equal to the jth column in this matrix. So if I take the jth column, what do I get? I get y. Now I have to be careful, because if you go over here, you'll see it's going to be yj, comma, let's make sure y1 comma j, all the way down to y n plus 1 j, right? It's basically taking this matrix, and I'm stripping out the jth column in this thing, right? And then if I do the same thing with, I can erase this, I don't really need this anymore. If I do the same thing with u, I can say that, I can call, let's say v, 1v is equal to, so let's say u, 1 colon n, is equal to v1 up to vm, where vj is equal to j1, all j1, 1 comma 1 comma j, all the way up to v n comma j. Right? So all I'm doing is, again, I'm stripping out the jth column of the matrix U. So, and then I have T0 and Tf. And finally, we have the scalars T0 and Tf. So my NLP decision vector Z would look like this. Remember, I'm stripping this all into a large column. It's going to be each of those values of y, these yj's, all stacked on top of one another, right? So it's going to be y1 stacked on top of y2 stacked on top of yn, and then u1, and then all the way down to well, let's be a little more explicit, u2, all the way down to v1, v2, up to vm, and then t0, and then tf. This is the input to the NLP objective and constraint function. In other words, what's going into the NLP objective and constraint function is this vector z, not these matrices. It doesn't know anything about matrices. It does everything with vectors. This is what's going in, so this is what I have to start with. So what you do then, once you do that, once you've created that, is now you strip off from each of those parts of the NLP decision vector that correspond to the states and those that correspond to the controls, right? So you say that z, x, there's a portion, so let's suppose I write z this way. I say z is equal to a bunch of variables that correspond to my state, a bunch of variables that correspond to my control, something that corresponds to my initial time, z t0, and something that corresponds to the variable that is my final time. So what are these different pieces? Well, zx is going to equal z1 all the way down to what? Well, what's the last value in here? Well, we know what the last value is because we know that matrix, which consists of the states, is n plus 1 by n. So the last value here is going to be z n times n plus 1. It says that the first n times n plus 1 components of the vector z correspond to those values that consist of the states, right? And then I do the same thing for z sub u, which correspond to the controls. It's z n times n plus 1 plus 1 all the way down to z. The last one is going to be n times n plus 1 plus what? Plus it's going to be m times n, right? Because I'm going to start where I left off. The first value that corresponds to the control is one more than the last value that corresponded to the states, right? So the first n times n plus 1 of these corresponds to the state, and then the next m times n of them correspond to the control, and then you say z t0 is equal to z of n times n plus 1 plus m times n plus 1, and then z tf is equal to z n times n plus 1 plus m times n plus 2. Does that make sense to everybody? Yeah? Okay? So what I'm trying to help you with here is a little bit more of the practical aspect of this. It's like, if you were going to implement this in an NLP, what would you need to actually do? So if you take an NLP solver like SNOpt, or you take an NLP solver like fmin-con, it doesn't matter. There are some details in here that are going to be very specific to the particular NLP solver that you're using. Certain NLP solvers require things in a slightly different format than others, but this is the general procedure for all this stuff, okay? That you still need to do all these steps. So now I have all these NLP variables, but you see here that these are now vectors, right? I erased it. My Redau pseudospectral method doesn't work with vectors in its native form, right? It works with these matrices and these values of the state at different points in time. So what we do now is we take each of these and we reshape them into matrices. So we say zx, what we're going to do is we're going to do a reshape. And the reshape is going to change this from a vector of length n times n plus 1 to a matrix of size n plus 1 by n. And what we get out of that is we get this vector x1 colon n plus 1. So all a reshape does, it says take the elements and put them into a different configuration from what they're in now. Right now they're in the form of a column vector. But what I need them to be is I need this to be an n plus 1 by n matrix. So literally, I kid you not, okay, in MATLAB, this is what this would look like. You would say x is equal to reshape zx n plus 1 n. And it does the reshape for you. And it puts it into the format that you would have. Now this, remember, contains all of the values of the state. It contains the state at the Redal points plus the state at the final point, right? Because it's got the last value. And at n plus 1, that's the value at the final point. But you remember that the collocation equations, the left-hand side contains all these values, but the right-hand side only contains the values at the n Redal points, right? Because that differentiation matrix for Redal is not square. It takes in, it has one more column than it has rows. So when you apply the differentiation matrix to x, you're going to wind up getting a vector of length 1 smaller, or a matrix of length 1 smaller. It's going to have one fewer rows than what came in, right? So d times, so x is an element of Rn plus 1 by n. But if I take d times x, well, let's use MATLAB notation again, d star x, that is an element of R n by n, because d is not square. It's a rectangular matrix, right? So the right-hand side, so what I do is I would create a new variable for the right-hand side. I would say x RHS is equal to x 1 colon n comma colon. I'm using MATLAB notation here. I hate using MATLAB notation in class, all right? But if it needs to be this explicit in order to be able to make it clear, that's what I'm going to do, right? It says, give me the first n rows of the variable x. That's what that says, right? Give me the first n rows and all the columns of the variable x, right? X is this up here, which is n plus 1 by n. So this only gives me the values at the Redal points. So then what I would do is I would plug this in to get my right-hand side. So what I do is I have some right-hand side function. So I would say, you know, the right-hand side of the ODEs is going to equal my function f evaluated at x RHS, whatever that happens to be. This is going to give me the right-hand side of the dynamics. I have to code this. I mean, it depends on your problem. This is the problem-dependent line right here, right? This depends on what your differential equations are. So the next thing you have to do is you have to code the cost, right? Well, the cost is really easy to code because the cost is, by definition, you're going to have some objective, you're going to have some Lagrangian. So what we do is we say, let L be the Lagrangian of the optimal control problem. And we're going to let phi equal the Mayer cost. So what you do is you say, well, x init, which is my initial value of the state, is going to be x 1 comma colon. It's the first value of the state. X final is going to equal x end comma colon. That's an n. E, N, D. Okay, you could put n plus 1 in there if you want to, right? But I know it's length n plus 1, so when I pull off the last row, it's just the n. That's a reserved order in that line. So you can do it. Or, if you don't like doing it that way, you can say equals x n plus 1 colon. Gives me the first value of the state and final value of the state. Now I have the first and last values of the state. So now I say phi. Oh, actually, I got to get the. Oh no, I have the times, right? So I say phi, or so I could say Mayer. Let's call it Mayer is equal to phi of x init z t0 x final z tf. There's my Mayer cost. I'll just evaluate it. Now again, this is a user-defined quantity. You have to tell me what your Mayer cost is, right? Now I've got to do the Lagrange cost. Well, I know that L is going to equal, well, let's not do this. Let's call it Lagrange. Is going to equal L evaluated where? Where is L evaluated? Remember that the cost, the Lagrange cost function is only evaluated at the Redau points, right? It's not evaluated at the final point. So it's going to be X, RHS, U, and ZT0 and ZTF. So that evaluates my Lagrange cost. And then what I do is my cost, which I'll call it J. Let's just call it cost. Cost is going to equal Mayer plus W transpose, do it in that way. W transpose star Lagrange. This is a vector of LGR weights, which I'm going to denote as a column vector, so I'm taking its transpose. That's a transpose there. I just didn't put a T. I put an apostrophe because the transpose operator is an apostrophe. All right? So this gives me my cost function, and now I can evaluate, I can get my, I forgot to put this here. So I put D, I have to put something else here. Defect is equal to D star X minus ZTF minus ZT0 over 2 times RHS. That gives me my defect constraints. So these defect constraints, but they're not the right size, so I have to reshape them. What's the size of those defect constraints? Anyone tell me that? I just went through it. What's the size of these defect constraints? It's capital N by N, right? But remember, in my NLP, which I've erased, those constraints are not matrices, right? They have to be vectors. So what I have to do is I have to take the defect constraint and I have to reshape it to a what? An N times N by 1 matrix, a long column vector, right? To give me a new defect constraint. Call it defect column. Right? So that would look like this. Defect column is equal to reshape defect N star N, comma 1. It reshapes it back into a matrix, to a vector from a matrix, right? So now I've reshaped that into a big column vector. And now any inequality constraints that I have, if I have boundary conditions, you see how I evaluated the Mayer cost? I evaluated it with the initial and final state. If I have boundary conditions, where are the boundary conditions applied? They're applied at the initial and final point. So they have the exact same form as this, right? So if I say my function, say let, I don't want to call it phi because I called it, let b equal boundary condition function. Right? Then my boundary conditions, BC, will equal B evaluated at X init, X final, T0, and TF. And again, that's a user-defined quantity, right? So that gives me my boundary conditions, right? So now I have my boundary conditions. And then I do the same thing with the defect constraints that I did with my path constraints. If I have path constraints, if I say let C equal the path constraint function, then my path is going to equal C evaluated at X, right-hand side, U, Z, ZT0, and Z, TF. And then this, of course, is going to be the wrong size too, because it's going to be a matrix, right? So if I say the number of path constraints is P, right? Let's say Q, right? Let's say I have Q path constraints. Then what I need to do is I need to take path, and I need to reshape it into an N times Q by 1 to get me a path column. So my path column command is going to equal reshape path N star Q, comma 1. Right? Then what I do is I say my full vector of constraints, so k, which is my full vector of constraints, is going to equal defect column, path column, and what I call it? BC, my boundary conditions. I just stack them all on top of one another, right? Because this is a column vector, that's a column vector, and that's a column vector. They're all column vectors. I can stack them all on top of one another, right? So that gives me this is my constraint. This is what I'm calling. Remember I called K the combination of F and G, right? These are equality constraints. These are inequality constraints. They could be inequality constraints, right? Because the path constraint doesn't have to be an equality constraint. It can be an inequality constraint, right? And that's how you pass information back and forth between the form that you recognize as being from the continuous problem, where you've discretized the continuous problem and you have a state at a bunch of points in time, to the NLP. The NLP doesn't know anything about your optimal control problem. It doesn't. All it's doing is solving a nonlinear optimization problem. It could care less where it came from. All it says, you gave me these functions, I'm just going to try to do what you asked me to do, which is minimize this cost subject to these constraints, and it's going to try to solve that problem. What the problem is that you're trying to solve, the nonlinear programming problem solver knows nothing about. It has absolutely no knowledge whatsoever. Okay? So this is the procedure to go back and forth between the two. And the reason I bring this up is because this gets confusing, because when you're trying to implement something, you're dealing with two distinctly different entities. One is the optimal control problem and its discretization. The other one is the nonlinear programming problem. And what I was trying to show you was that when you discretize using these methods, you get a system of equations that needs to be satisfied, but you need to do it minimizing a cost. That becomes a nonlinear programming problem. It's a nonlinear optimization problem. That, in and of itself, has nothing to do with optimal control, the nonlinear optimization part. But it comes from an optimal control problem, right? Whatever this NLP is that you're solving comes from a nonlinear optimization problem. This is, I spent last week, it's kind of weird, I was sitting there, down in the South Caribbean, and I'm sitting there giving all these lectures on optimal control, and I'm like, wow, this would probably be pretty useful for my class. So I've never actually done this in my class, because normally when I'm teaching these short courses, I'm teaching it to people who are kind of sort of more industry types. They're interested in just using it. They're not interested in any of the theory. And in the class here, I spent a lot more time on the theory because I wanted you to see where everything comes from. And I spent some of the time there too doing that, but I spent a lot more time trying to get into implementation. But I realized that if you don't have a handle on how to implement some of this stuff, then it gets confusing, because you don't know what it is that you're trying to do when it comes to the actual software. And if you're trying to solve a practical problem, like some of you, may want to use some of this stuff for your projects, and if you don't understand how to do it, then you won't get there. Now, given what I've done here, you should be able to make a correlation between what I've done here and what I gave you when I sent you that MATLAB code. I sent you a bunch of MATLAB code where I implemented a couple of the problems that we had solved in class. Right? You did the brachistochrone on the exam. You did that orbit raising problem on the exam. I gave you those same examples. Two of them are the same. And then I gave you another simple one-dimensional optimal control problem, so you could see how it works in an even simpler case. Because the brachistochrone problem is 3 states, 1 control. The orbit raising problem, I think, is 4 states, 2 control with a path constraint, so it's more complicated. So that hypersensitive problem, which is in the middle, is one that has 1 state, 1 control. You can see what's going on in the simplest form without getting into too much complexity. That's why I put it in there, so that you can do that. Now, hopefully that will allow you to be able to see what's here and be able to see what I did. My notation on the board here actually is a little different from the notation I use in the code, but that's because I don't want to use it in the code. But the idea is the same, right? I mean, I'm doing that. You'll see reshapes. By the way, there's another thing in MATLAB. Part of this is like the art of MATLAB programming. And I'll just tell you, I've got a little room over here on this board, is that in MATLAB, if you do this, if you have a matrix, suppose let A be an m by n matrix, just some arbitrary m by n matrix, it doesn't matter what it is. You can actually get A to be a column just by simply doing A of colon. That makes a column vector. And the column vector is oriented so that the first column is stacked on top of the second column, is stacked on top of the third column, et cetera, all the way down to the end. That's the operator in MATLAB, because fundamentally, the way MATLAB works with vectors. Even when it's storing matrices, it's storing everything as vectors. And that's why you can do this. This is a command in MATLAB. This is equivalent to the command just saying colon A. It's the exact same thing. There's no difference. That actually is a reserved word in MATLAB, colon. So if you make a variable called colon, you've overridden one of the reserved words in MATLAB. So it'll mess up your MATLAB code if you actually make a variable called colon. So all of these things have like terminology in MATLAB. There's an actual word associated with this. I mean, you don't have to use the symbol. That symbol actually is a function somewhere in the MATLAB code that actually does that operation. So A of colon is the same thing as saying colon. So you can strip things into column vectors very simply just by saying A of colon. So if you want to get the defect constraints, you can do it the way I did it here, where I did a reshape. Or what you can do is you can just strip it into a column vector. Now you can't go the other way. Once you have a column vector, you have to actually do a reshape to get it back to be a matrix. Yes.
Do we have to make an initial guess?
Yes, that's the next thing. Okay, that's good. That you reminded me. I was going to forget about the initial guess. So in the NLP solver, now let's go outside the NLP solver for a minute, okay? So because this is the interface between the collocation scheme and the NLP solver. But now on the outside, what you have to do is you have to actually make a guess of this. So I'm going to leave some of this stuff up there. So now how do you make a guess? Because clearly you could make a guess a lot of different ways. But the way it's normally done is, this is how I do it anyway, but you don't have to do this. But it's as good as anything else. Is that, so let's say initial guess. Or NLP solver. So let's call this thing Z guess. All right, that's what I'm going to call it when I'm all done. All right, that's the end result of all this. But what we really have is in the optimal control problem, what do we have? We have x of tau, u of tau, t0, and tf. These are the things that we intuitively understand. We understand the state as a function of time. We understand the control as a function of time. So what you do is you normally use some really dumb initial guess. So usually we use a straight line initial guess. What does that mean? What it means is that, so we guess x1, which is the initial state, and xn plus 1. We guess u1 and un. And then what we do is we guess t0 and tf. And for these, we perform straight line interpolation. At the LGR points. So I know the LGR points because if I solve this for any particular value of n, I've computed the LGR points ahead of time, so I know what they are, right? So what you would do is you say, well, given values x1, xn plus 1, interpolate linearly between those two values using the interp1 command in MATLAB, and interpolate at the LGR points plus the final point. So that's what's actually the LGR points plus final point. And then what you do is you take all these, you stack them all up, and then you strip them all into vectors, and then you perform reshapes to get your vector z guess. So z guess would be I take these values at x1 through xn plus 1, I stack them up into a matrix, I reshape that whole matrix to a vector. I take u1 through un, I stack it up into a matrix, I reshape it into a vector, I stack it on top of the vector I created by reshaping this. And then I stack T0 and TF on top of that. That becomes my value Z guess, and I stick that into my NLP solver. That's what goes into my NLP solver. Does that make sense? Yeah. Okay, so that's how you actually do this. This is the procedure for it. And that's outside of the call to the NLP solver. Now, what I'm happy to do, really happy to do this because it's going to be helpful to you and it's just good learning in general, is that if any of you want to come to my office and want to get more clarity on how this works, we can do this a number of ways. If you would like to set up a problem with one of these, we could pick a simple problem and we could code it up from scratch. That's one way we can do it. Another way is if you want to take the code that I've written and you want to come and you want me to explain how different sections of the code actually work, I'm happy to do that as well. If you want to do a combination of the two, we can do a combination of the two, that's fine as well. If you want to use a different NLP solver other than SNOP, you'd rather use something like maybe fmin-con because a lot of you have access to the optimization toolbox in MATLAB, we can set it up with fmin-con. The syntax is slightly different in fmin-con, but essentially it's the same. I mean, you still have to code an objective function and a constraint function, but the way you go about coding it is just a little bit different because of the way in which fmin-con interfaces with MATLAB. It's a little bit harder to work with fmin-con than it is to work with SNOP because SNOP creates, in fmin-con, the problem you run into is that the constraints have to be of the form, the inequality constraints have to be of the form, C inequality is less than or equal to 0. But in reality, a lot of times you have constraints that say C has to be between C min and C max. So when you have to code C less than or equal to 0, you have to do C minus C min. C minus C max is less than or equal to 0, and then C min minus C is less than or equal to 0. You have to stack that into a double vector in order to be able to get it to work. So that's an implementation issue. That's just the way fmin-con works. I don't know why it's coded that way. It's not a very good way to code. Because you're coding the same function twice in order to do that, which is not a good way to code. But nevertheless, that's how it works. And I mean, but barring that simple implementation issue, the rest of it works pretty much the same. So it's not that hard. But I'm happy to do this, and I'm hoping that in the next, we've got about a month of classes left. So what I'm hoping for in the next few weeks is that I intentionally went through all of this material earlier so that I give you enough time to be able to think about how you might want to use some of these methods on projects. I went through shooting, multiple shooting. I went through both direct and indirect, and then I went through all these collocation methods so that you could get a survey of what kind of method you'd actually want to use to do your project problem. My recommendation for your project is that you don't start by trying to solve your project problem. Start by solving a simpler problem. Make sure you can get it to work. Make sure you can reproduce what you know the solution to be, and then modify it to do the problem that you actually want to do. Because if you're trying to do something for which you don't know the solution, and you plug it into an NLP solver using one of these schemes, you have no idea whether you're doing it right or wrong because you have no experience with it prior to that. And so that's not a good way to go about doing it. So set up, at least, I would recommend 2 or 3 problems using one of these methods, right? My recommendation is Redout because it's just the easiest one to use if you're going to do collocation. And set it up, and if you have trouble like figuring out how to compute like the differentiation matrix or how to get the weights, all of these things are actually available on the MathWorks Central File Exchange. There are people who've written codes to compute the LGR points and weights. There are people, there's this one, actually I say people, there's one guy actually who's done this all. His name is Greg Von Winkle, and he apparently got his PhD several years ago. I think he was either University of New Mexico or New Mexico State, I don't remember where. But he put all this code that he did from his PhD thesis on the web because he was doing all this stuff with spectral collocation. And so he's got LGL, LG, LGR points and weights, and then he's got this function called colloc-D, which actually does differentiation on an arbitrary grid. So he actually figured out how to do all this stuff. And I could show you how to use all those things, but you can get them all from the MathWorks Central File Exchange. They're all freely available, and you can use them for your homework and for your project. That's what we all use. We don't compute all these things ourselves. It's too much work. And actually, his routine that does the differentiation matrix, you have to be a little careful with it because it always computes a square differentiation matrix, and depending upon which is the non-collocated point, you have to lop off either the first row or the last row of the matrix. So if you use the LGR points plus the final point, then what you do is you stick all those in, you have a vector of length n plus 1, you can compute the differentiation matrix on that grid, But in order to get the right differentiation matrix, which is n by n plus 1, you've got to lop off the last column, I mean last row, because the last row is the non-collocated point. It's actually a really easy thing to do, but you have to know to do it, because it'll give you back a square matrix. So the thing about all this is you just have to be, we started a couple minutes late, so I just want to finish this slide. The thing that you have to keep in mind is that all of this stuff takes a little bit of practice, which is why I wanted to give you a little bit more time so you could practice it, because the last thing I wanted was all of you to be towards the end, rushing, trying to figure out how to do all this stuff, and the project is due in like a week, because the project is due at the end of the semester. So I don't want it to be that late in the process and you have no time to be able to do any of this stuff. So the way this class is going to work from now on is that we're pretty much done with collocation methods. I'm going to go back now through some slightly more special topics that I didn't cover earlier. Remember, I said I was going to talk about path constraints, and I'm going to talk about some other things. We'll talk a little bit more about singular arcs, and we'll talk about multiple phase optimal control problems. These are things that I didn't consider to be like worth discussing earlier in the semester, because like I said, I wanted to give you enough time so that I could lay out all the methodology so that you could use it. Now that we've done all that, these other topics will be easier to digest, because now you say, okay, I don't need to worry about all the methodologies done with all that. We're going to go back to some of these topics, and it's going to augment, what we've already done. So by the time we're finished with all this, we'll have a complete picture of both the theoretical and the practical side of optimal controls, both the numerical methods and the theory. That's where we're going to go from here. Okay. So if you have questions, I really want. I don't see anybody in my office. Nobody ever sends me emails saying I want to like talk to you about project work, or I want to get help with homework. And I feel like the Maytag repairman. It's like nobody comes and asks me for help. So if you really need help or you're confused about something, please come and ask me for help. I'm like more than happy to help you. This is a really interesting subject, but it's also a very hard subject, and I'm sure that at this point, all of you realize that this has not been